Today, we're going on an incredible journey. We're heading into the heart of one of the biggest, most powerful construction projects on planet Earth, the building of the Himalayas. I mean, really think about that for a second. How do you build mountains that scrape the sky? We're not talking about bricks and mortar here. We're talking about forces so massive they can buckle and lift entire continents. So, how in the world does that actually happen? Well, it all starts with a collision. But this isn't some quick car crash. This is a collision happening in ultra-slow motion between two gigantic continents over millions and millions of years. It's a process so slow it makes a glacier look like a race car. To really get a grip on how these mountains got here, we've got to understand that crash. We have to rewind the clock way back to a time when the Earth looked totally different. Okay, so picture this. About 180 million years ago, there's this massive supercontinent called Gondwana. It starts to crack and break apart. One of those pieces, the landmass that would become India, breaks off and starts cruising north. For tens of millions of years, it's just chugging along across an ancient ocean. Then, around 50 million years ago, bam, it slams right into the Eurasian plate. And that's when the real action begins. So, to really understand this whole process, I thought, why don't we go on a little trip, a virtual trek? We're going to hike right through the Himalayas, starting in the south and heading north, beginning in the very first ripples of this mountain range. This diagram here is basically our map for the journey. You can see we're starting way down here on the flat Indo-Gangetic plain. And our first objective? It's that first band of hills you see rising up from the flat ground. That's the Siwalik range. Now, what's so cool about the Siwaliks is that they're basically the Himalayas recycling themselves. I mean, think about it. All the rock, sand, silt, and mud that erodes from those giant peaks way up north has to go somewhere. It gets washed down by rivers and dumped right here. Over millions of years, it gets compressed back into rock, and the same collision that's building the main range folds and lifts these hills up too. And as a bonus, all that buried material makes this area an absolute goldmine for fossils. Okay, before we climb any higher, we've got to get our heads around one really key concept. This is the main engine building everything we're about to see. It's called a thrust fault. The best way to picture it is to imagine you have two big, thick rugs on the floor. Now, what happens when you try to push them together? They don't just meet neatly, right? One of them always starts to bunch up and slide over the other one. That is a thrust fault, but with continents. And this little sketch shows it perfectly. You've got one block of rock, the hanging wall, being actively shoved up a ramp and over the block below it, the footwall. It's that simple. But this one movement, repeated over and over on a massive scale, is what thickens the crust and shoves the mountains toward the sky. So keep that image in your head, because it's the key to everything that comes next. All right, you got that? Thrust faults. Good. Now let's see what happens when this engine goes into overdrive. We are officially leaving the foothills behind and climbing into the big leagues, the real giants. Looking at our map again, you can see our path is about to cross some of these major lines. Now, these aren't just lines on a diagram. These are enormous fault systems, almost like superhighways where huge masses of rock are on the move. We're crossing from the Siwaliks into the next zone, the Lesser Himalaya. And there are two main players you really need to know about. The first one is the main boundary thrust, or MBT for short. That's the fault that divides the foothills we just left from the Lesser Himalaya. Then, as we keep going north, we hit the next big one, the main central thrust, or MCT. This one is the gateway to the really high peaks, the higher Himalaya. Now, these faults aren't just one clean break in the rock. Oh no, it's way, way messier than that. They form these incredibly complex layered networks. This diagram shows something called a duplex structure. A great way to think about it is like taking a deck of cards and squeezing it from both ends. The cards will slide over each other and the whole stack gets way thicker, right? That's exactly what's happening to the crust here, causing that massive uplift. So you can imagine, as these huge slices of rock get stacked up and buried deeper and deeper, something pretty dramatic starts to happen. They get subjected to incredible heat and immense pressure. This whole process is called metamorphism. Honestly, the best analogy is a giant geological pressure cooker. It literally bakes the original rock and transforms it into something completely new, like turning a simple mudstone into a tough slate or a sparkling schist. And all of this, the stocking, the pressure, the cooking, it leads us to one of the greatest puzzles in all of geology. For decades, scientists climbing through these mountains kept finding something that just didn't make sense. something that seemed to break the laws of physics. So what was this baffling mystery? What on earth did they find that had them scratching their heads for so long? Okay, here's the problem. It's a basic rule of thumb in geology. The deeper you go, the hotter it gets. Simple. So you would always expect to find the most cooked, high-temperature rocks at the bottom and the less cooked, cooler rocks on top. But in the Himalayas, right along that main central thrust, they found the exact opposite. The super hot, high-grade rocks were sitting right on top of the cooler, low-grade ones. It was completely upside down. This bizarre phenomenon is called inverted metamorphism, and it's like finding a layer of ice at the bottom of a boiling pot of water. It just shouldn't be possible. For geologists, this was a massive puzzle. How do you get the really hot stuff from deep down to end up on top of the cooler stuff? Well, that puzzle kicked off some brilliant scientific detective work. This slide shows two of the leading ideas that came about. On the left, you have what's sometimes called the hot iron model. It suggests that a giant slab of rock that was already hot got thrust over the top of cooler rocks, basically acting like a giant hot iron pressing down on them. On the right is the shear heating model. This one proposes that the intense friction from the rocks grinding past each other along the fault itself generated enough heat to create this weird upside-down pattern. It's a fantastic scientific debate. Now, it's time for the final leg of our journey. We're crossing the high peaks, heading north towards the vast Tibetan Plateau. And it's up here that we find the literal scar of the collision, the exact place where two worlds finally stitched themselves together. This boundary is called a tectonic suture. It's the geological seam that marks the final resting place of the ancient Tethys Ocean, which once separated India from Asia. This is it, the evidence of the crash we've been talking about this whole time. So how do we know a whole ocean was once here? Because geologists found the clues. They found things called ophiolites, which are basically slivers of old oceanic crust that got scraped off and smeared onto the continent during the crash. They found deep-sea sediments, and get this, they even found marine fossils, all stranded thousands of meters above sea level. The evidence is literally written in the rock. So after this incredible 50-million-year story, you might think the action is over, but it's not even close. The collision is still happening right now. The Indian plate continues to bulldoze its way into Asia, forcing the Himalayas to grow taller by about 5 millimeters every single year. And all that constant pressure is what builds this seismic tension that makes this region so prone to earthquakes. And that really brings us to the final, amazing thought. This isn't a story with an ending. It's a geological epic that's still being written, millimeter by millimeter. It makes you wonder, doesn't it? If this is what the first 50 million years of this collision has created, what on earth will the roof of the world look like in another 50 million years?